Good morning, everyone. I'm Marcelo. I entered Shape last month as a data engineer on the DBMS team, and I'm now at the predictive maintenance team. And on today's ShareOut, I'm going to present a data engineering framework that we developed on DBMS to refactor the data layer. And in case you have any doubts, feel free to raise your hand. I'm watching the participants list, or just to ask. There is no problem. Okay, I will share my screen. Okay, so let's begin from the very beginning. What is this data layer of an application that we are calling here? Well, to answer this question, we must first ask, what do we use data for? And this is a simple question and the beginning of our line. It is not an exhaustive list, but we could sum up to descriptive purposes, diagnosing something, predicting what will happen, or prescribing what should we do. So these four uses of data is some that justify for example, the construction of a dashboard, or indicating an action to be done, or describing a problem so that we can think on a solution. Basically, it is all around decision. The main usage of data is around decision, making decisions or understanding decisions, consequences. And here at Shape, data is the core of the business, and this is no novelty for anyone. As on these two examples behind the PDM in Flow or the DBMS interface, we have a data layer, we have a database, we have tables, we have a process where this data passes through to get to this visualization that will help make decisions or changing the business of our clients. But where is this data? When we see this interface, we access this data, we can filter, we can apply rules, but where this data comes from, how is it stored? Basically, generalizing, we could resume data storage into two alternatives or two types. We have file system storages, the one in the left, and we have structured databases, the one in the right. There is other alternatives. There are unstructured databases. There are other alternatives, but here let's simplify to these two alternatives: a database, a relational, structured, and a file system. When we talk about accessing data from an application, just like the former examples, the inflow and the DBMS, or an app in our smartphone, building a dashboard, or other type of consumption that require low latency response, which means when I demand the data, I cannot wait too long before having the results accessible. We're likely to be consuming from a database, the one in the right of our slide. It is mostly a table with structured, organized data that has fast response, so that when I query, I have the results in a small waiting period. So the database is generally used for structured data, generally in a tabular form. And this presumes that our data can be typed. I can have fixed types for my columns. I have columns organizing this data. Is a tabular form. The file system, the one in the left, is more general and have no much requirements has no much limitations of extensions of how the data can be stored. It's just like the hard drive of our computer. We can put anything we want in there using the organization pattern that we want with no restriction of what to put or where to put. So it is more general and it is generally cheaper as well. It can be a local storage, just like the hard drive of our computer, or it can be cloud-based, just like Google Drive, for an example, or Microsoft OneDrive, or even an Azure blob storage that has a more that has a application more to the business, to a product itself, and less to a consumer like us on our daily basis that we're going to favor a OneDrive, a Google Drive, and other interface accessible storages, cloud storages. So when do I choose one over the other? When do I go to the file system and when do I go to the database? It's not always a straightforward question. As we'll see further on, there we'll pass through some examples, but generally speaking, databases are more expensive and require this tabular form or this structured form that I mentioned. So to store large amounts of data, it is generally best to store on a file system when this data is cold. And cold in this context means that this data is less accessed or can tolerate a higher latency. So when I require this data, I have no problem in waiting a few minutes to have it available, for example. And this is not a good approach for a dashboard. The customer will not wait for a minute to the dashboard load on the screen, but if I am querying the data, if I am an analyst, or if I'm building a machine learning model, there is no problem. I wait 1 or 2 minutes for the data to be available. As code means higher latency or less frequently accessed, hot, on the opposite, means that this data is highly accessed and requires a low latency. So bringing it to our daily life, the cold storage is like the exams of my childhood. If I have them still on my house, I will keep them on a closet high that I have no problem in getting a ladder and climbing to get it when I need, if ever I need, because I will look at it less than once a year. On the opposite, my credit card or my identification document is a hot information. I need it as soon as I am required. If I'm on the street and I need my documents, it has to be with me. I need to get it on the site. I can't go home, pick the document and back to where I was. So another criteria to evaluate when to choose one over the other is that file systems accept easily data unstructured. There is, as I said, alternatives to store unstructured data on databases, but generally, and we're simplifying the point here, file systems accept better a unstructured data, such as files of any kind, non-tabular files or binary files, or even textual files or files that are tabular like CSVs but have no format predefined. Well, no matter how data is stored in one or the other, it must pass by a process to get there. Data just won't appear on this folder, on this or on this database without coming from somewhere and passing through some process. And this is pretty obvious, but how then is this data loaded into one or the other of these two structures. And here we begin to enter the role of a data engineer more properly. The data engineer will be the guy that extract the data from somewhere, apply the needed transformations, and then load this data somewhere else. And this is what we call ETL, this three-letter word, which stands for extract, transform, and load. Data can come from a variety of systems and ways. It can come from an API, a database connection, a file landing on a specific folder that we're looking at. And we will need to create a script to get this data. We will knock on a API and get the data, save somewhere else, or we'll connect to a database and pull this data out, or build a script that will open this file and parse its contents so that this data can be interpreted and used. After understanding the data, and understanding is a cost, it's a rather underestimated and important phase of this process. So we have the data on the source, we get the data, we must understand what we're going to do, what is there on this data, how to use it, and then make it available in other file system or a database after applying the needed transformations. So it is often common that data is not cleaned, that data is not accurate, it's not on a optimal format, and transformations are needed to make this data trustworthy and useful without questioning much of the contents. So after these transformations, then we load it into the next storage option. Generalize, because we're going to dig a little bit into that ETL step right now. So this is a general traditional data architecture. We have multiple sources here on the left. It can be a Google Analytics API or a Facebook API. It can be a file storage system or a Salesforce or an SAP that are ERPs that have the business data or data from other partners. We have multiple sources of input data, and generally we will need some script of some form to connect to this data source to get the data and make it available. The traditional data architecture using relational databases would be to get this data that must be rather structured, loaded into a database on a stage table, and the stage table is a temporary table that will receive this data already in a tabular form, already pre-typed, and then this data would pass by a storage procedure to a final table. And let's just stop a little to look at these blocks, these concepts. We have here a scheduler orchestrator. There is the responsible for triggering each part of this pipeline, each step of this pipeline. So I can have a process to get data from SAP daily on a daily basis. And this scheduler will be a platform where I schedule this process to run daily. And then this platform will daily trigger a script that goes on SAP and extracts data. It is kind of an agenda. And this data will be processed by some unit. And here we're using general terms for everything. Then further on, we'll get to the actual platforms we use on our architecture. This processing unit is a machine of any kind, just like our computer, that will have a script on its hard drive or accessible from this processing unit. And the scheduler will say, well, run this script now. The processing unit will then process this script and generate an output. Here on this architecture, this processing unit will, for example, open a file, parse its contents, and load into the stage table of a database. The storage procedure, well, the name already tells a lot of what it means. A storage procedure is a script stored inside the database. It can have other purposes, but here we're using it as a script that will get data from one point and transform it and load it into the other, a small tiny piece of the ETL process. Here, the whole pipeline, which is data coming from here and getting here, or on this database, will be orchestrated by this unit, will be processed by this unit, and then once into the database on the stage table, will be processed by the very database. The database have a processing unit inside, as well as the storage. Differently from a file system that only stores, the database can process as well. So the storage procedure will run inside this database environment and apply all the transformations we need for this table, for this data to be trustworthy and to be available on the format that our business requires. So if I'm going to train, for example, a model, I can create features here. I can create lately, but I can also create here. I can drop columns, create columns. I can remove unnecessary data, and so on. So this is a traditional architecture. But why do we say traditional? Because this works rather well for a structured data environment and within a reasonable volume. But there are some counterparts that we'll get to soon enough. But when we transition to a big data scenario, this architecture no longer performs so well. And Shape is all about big data. So big data, on a conceptual definition pretty briefly, is generally pointed to these five V's: volume, variety, velocity, veracity, and value. We're talking about large amounts of data which has a great variety that must be trustworthy to be used, must be processed with haste to achieve real value. This is a conceptual definition, but helps understanding the data environment we expect when working with the so-called big data. And here at Shape, for an example, on DBMS, we have data coming from the SAP with information about processes and tags underneath the bow-tie barriers that we must update frequently so that the operation and the customers can see what they need to act on to make the processes safe, to make the operation safe. On PDM, we have sensor data that feed the models, feed the training of the models, the predicting, so that we can point when a equipment will fail, and so that the customer can realize a predictive maintenance instead of a reactive maintenance that will cost a lot more. On DCT, we have other kinds of data. We have not all of them so structured, and well, there are a ton of use cases, and it's a lot of data. So how do we process, distribute, and organize all this data, keeping costs under control and allowing scalability? For this, we will need a different proper architecture. And this is a general data architecture. And next, we will see how we implemented this using the Microsoft Azure resources on our use case. You might notice that the beginning and the ending looks pretty much the same with the traditional architecture. We have the input data, the processing unit that loads this data. We have the applications, dashboards, and analytics connected to a data warehouse. It was called a database on the previous slide, but essentially, let's keep it simple, a data warehouse. The main changes are at the core of the solution. Instead of having a database with stage tables and storage procedures here in the middle, we have a file system storage where this data will land, pass through transformations, and be available to be loaded into a data warehouse where it will be consumed with low latency. So the aspects we talked about on the beginning about latency keeps the same. If I need low latency, I need a database generally. If I can tolerate a higher latency, I can store it on a file system storage where I will have a lower cost, and I can also achieve a higher processing capacity with a comparable, a cost comparably lower with a database. We still have our orchestra here triggering all of the processors. And a major difference here when we replace this file system storage, the database by this file system storage, is that we can store more data costing less. And also we can split the data transformation process into different layers so that tracking changes or implementing changes or tracking problems is easier than when I have only one source of data. On the previous architecture, once the data was loaded on the stage table and to the stage table into the final table, the stage table would be cleaned out because it was a stage, a temporary storage, so that data entering would get there and after being processed would be removed from there. So I have only one source of where to get this data. It is the final table. And if I have any problem with this data, if some of the business rules I applied, if a cleansing part of my process was not that accurate, but passed through the development process and later on I perceived, I cannot rebuild the original data. I've lost this data after passing through the storage procedure transformations and loading into the final table. So if I need to rebuild my data environment, I will need to get to the source again and get all the history back. And this is not always possible. It is sometimes possible. If I'm speaking about an SAP, for example, I can get there and extract all the history, but I cannot look back at all the sensors history data available on a database necessarily. There might have architectures that allow, but not necessarily. So a better approach is to store this raw data that I received on a raw folder. We call layers these folders we have here, and they are folders just like the folders of our computer. We call them layers. We have a landing layer where files will land. So a third party, a partner of the company will send me an information via file and will save it on a specific landing folder that I give him access to. Frequently, I will look at this folder, get this data out of there, and put on my raw folder. The raw layer is where we store data as it came to the data lake, to our file system storage. The landing folder aims to be empty, so it is, as the stage table, a temporary folder. After data is on the raw layer, we can transform it and clean it and apply some standardizations to move it to trusted layer. On raw layer, we do not allow any modification of the data. But moving raw to trusted, then we can start transforming, but mostly applying cleaning processes, standardization of the nomenclatures, for an example, typing the columns if the data is already structured, so that the data is trustworthy. So that when I consume data from the trusted layer, I know that data can be used without questioning its quality. And just after trusted and moving data to refine it, we start applying business rules, aggregating the data, filtering and reducing its dimension so that we can transform it to a particular use case, to a table that will be needed for a machine learning training, for an example, or for a dashboard that will access it through a database. So splitting the ETL process into these 4 layers give us a lot more control over what's going on with our data, an easy way to track the changes and even implement changes. If I'm consuming the data to make a dashboard and I realize it has a flaw, it has some part that is not accurate, that has an error, I can go back to the pipeline, to the step of the pipeline that moves data from raw to trusted, and clean the data there, so that this cleaning will pass through, refine it, and through the database, and the dashboard will receive clean data, and also all other customers of this data that consume or directly into the data storage or on the database. And here there is a extra concept. There is the data lake. This structure here we call a data lake. It is a file system storage where we store large amounts of data, not all of it on a structured format. We can have multiple unstructured data on the raw layer waiting to be parsed and structured for further use. And this consists of a data lake. Basically a sink to all the data we have, and this is why we call it a lake. Well, and this is the blueprint of a generic architecture to process big data. It is valid to notice that these layer names might be found on different articles or different authors with different names, but the meaning and the steps between one and another are pretty much similar. We can find, for an example, a raw and landing mixed up into one layer. We can find trusted as curated. We can find, well, there are tons of names that we can see here: bronze, silver, and gold. There are other nomenclatures, but this one that we used is one that makes clear what is going on and how is the state of the data once it's in this layer. Now let's swap some of these blocks and name them accordingly to the platforms we have on our Azure environment. So this is basically the architecture we implemented on our DBMS solution. We have Azure Data Factory as our orchestrator. It is valid to mention that Data Factory is not limited to orchestrating processes. It has other features as well. It has, for example, a processing unit alternative inside its platform. But here we're using it mostly as an orchestrator. And as an orchestrator, it can register the logs of what's going on. It has a visual way of coding the pipelines as blocks that we can see in a process approach. We have Databricks as our processing unit. Databricks is a platform we're going to talk a little bit further on. that runs with a state-of-the-art framework of processing called Apache Spark. We have Azure Blob Storage as our data lake. Is a file system, a cloud distributed file system. And we have Azure SQL Server as our data warehouse, the layer where applications, dashboards, and analytics will consume data from. Ideally, our machine learning applications will consume data from the data lake directly, as it's cheaper than consuming from the database and can tolerate a higher latency than an application. So, what are the advantages that we have with this architecture? By using Databricks that underneath has this Apache Spark framework, we can have a higher processing power with a lower costs than a database. If we match one-to-one the processing volume of a database with a Databricks cluster, the Databricks will be a lot cheaper than the Databricks will be a lot cheaper than the database. As this framework called Spark is accessed through Python or Scala or SQL, we can program using all of these languages inside Databricks and sometimes all at once. We have a lot more liberty to implement consistency mechanisms and error treatments that are harder to achieve with pure SQL. When we were talking about storage procedures, for an example, it is harder to create a generic code architecture that will serve to implement these error treatments and auto-resolve mechanisms on our pipelines. As we're separating data into 4 layers, as I've said earlier, we have a clearer tracking of what's going on and a clearer path to implement changes. Also, because we're using code directly inside Databricks, this code is versionable on Git platforms, differently from a storage procedure that lies within the database. So to version a storage procedure, I must always copy and paste on a Git repository and realize that the storage procedure of the Git repository is up to date to what is inside the database. If I enter the database, alter and execute, and not copy paste, I won't know that it has changed. As we're using scripts connected to Git, there is no syncing problem between the whole solution repository and the scripts that load the data inside Databricks. And this architecture is also easier to scale because the processing capacity of Databricks is on demand. I can scale a database processing capacity on demand as well, but it costs a lot more if I need to jump from 250 to 500 DTUs of a database, for example, to double its processing capacity, than if I just add a node or two extra to a Databricks cluster to process a large amount of data. It's that point we said that the same processing capacity will be cheaper with Databricks, so scaling this processing capacity will also be cheaper. And also, when we're talking about replicating this to other customers, it's easier because the processing is decoupled from the data storage. I can have multiple Azure Blob storages for different clients and one processing unit, for example. Or I can have multiple processing units and multiple storages, but it is easier to move data around through the architecture because it is on a single resource that is the blob storage. We also have a reduced maintenance work as the code is concentrated into one single platform. We do not have code into the processing units and into the database and into SQL views and into SQL functions and other SQL features. We have them in scripts available to process by Databricks or any other processing unit we choose. And as we are saving data here on a optimized file storage format that Databricks provides, we can also have a native time travel, which means we store the table and its history. So if I change something on the today's load, I can go there inside the platform and load the yesterday version to see what has changed. And if I need, I can restore it. And this is native inside Databricks. It's a time travel feature that allows us to have a greater reliability on our environments. And if we have a disaster, a local disaster, we can recover using this native feature with no extra effort to implement as we would need if we wanted to achieve redundancy and this history within a database. And finally, last but not least at all, we reduce costs by moving into this architecture because the combination of these two costs less than this unit for the same amount. We're comparing when we are storing a petabyte of data, a blob storage will cost a lot less than a database, if possible to store it on a database. Okay, so this is the data architecture we implemented. But the presentation title is Data Layer Framework. Why call it a framework and not only an architecture? The data layer framework consisted of the combination of this architecture we just shown with the code libraries developed to support all Databricks processing steps. So instead of having a code written from zero on every step of the pipeline, as sometimes storage procedures requires us to, as I must repeat the table names because SQL is a little more verbose than an object mapping approach, such as I can achieve with Python and Spark or Scala. It was built a group of libraries, code libraries, that virtualized most of the ETL developing work. The processes doesn't change that much between one and another. I can have a large variety of input ways, but once the data is in the data lake, the transforming, the loading and saving steps are pretty much the same. I can load it as any file extension or through a connection, but I will save it overriding the Destiny table. I will save it with an upset approach, or I will just insert new data, append. There is a limited amount of options about how to save. There is infinite amount of combinations of how to transform that we can group and join with other tables and so on, but a limited amount of combinations of how to save. And these combinations of how to save with how to load defines how to reprocess a table, for example. And all of this was virtualized into a code that also encoded the standards of our data lake. One example, as shown on the screen, is the automatic naming and creation of external tables inside Databricks according to the paths available on the blob storage. So here we have an example of 7 tables stored on the refined layer of my data lake. This data lake of our customer have a structure that we'll see, a folder structure that was also defined as part of this framework, and we'll see on the next slide. But once data is saved to this location, automatically by this framework, by these code libraries, these tables are created inside Databricks to make it available to use it with SQL and by any other data engineer or data scientists that want to consume this data. This data is on the Delta format that I mentioned. Delta is the name of the format that stores the history and allows us to do this time travel. So by using this framework, I just wrote spark.etl.load, applied the transformations, spark.etl.save. Spark.etl is my library, and when loading, it's applied a bunch of transformations on the fly to optimize this loading. And when saving as well, to save less files, more compact files, to optimize the file storage options, and also creating automatically these tables. So we are reducing drastically the developing time of any pipeline when using this framework, and also maintaining a standard with all of the pipelines developed by several different data engineers. And this pattern that I've said of the folder hierarchy was also developed having scalability and reliability in mind. So here we have an example. We have the root name of our blob container, which is BMS because the application was called DBMS. We have any folder structure to identify our customer. So here we use two customers. We could use two folders. We could use other folder hierarchy. And just within these folders, we have our data lake layers, so that each customer is virtually separated from the other, and we can have them on different blob storages as well as on the same. If they are part of the same customer, for example, if we have a sub-customer of this major customer, of this major contract, we can have them on the same root folder, but with their layers separated so that data won't mix one with the other. And under the layers, we have our table folders, just like the ones I've shown on the previous slide. And this naming pattern is also maintained and enforced by the coding framework that we have. And now getting into a result of what has been done. This is a use case presentation. And now let's go to the use case of this data layer application. This was the existing architecture that we had. We had two different orchestrators, two different data factories with different parts of our ETL pipeline. The SAP being performed on here with one file system storage and one database. There were redundancy between data stored here and on the database. And we had a different part of our process being performed on another data factory, presuming manual transformations of the data as Excel sheets, and using a different SQL server that was costing twice, that would be consumed by our application. The whole pipeline that was not synchronized, one runs at a time and the other after a interval to ensure they would not conflict, but they were not linked together. The whole pipeline, if combined, would take 70 to 85 minutes. And the elements removed from the architecture costed $100,760 on last month. On the last month, it was observed before the refactoring to the new architecture. So there was a large stage tables stage here on the database. We had 16 temporary stage tables and 16 permanent tables storing all the history of the data that was also on this file system storage. And all of the code was splitted into storage procedures, SQL views, SQL functions, and it was not always clear when and where each transforming was being performed once we looked at the database. At the total, we had 25 storage procedures to perform ingestion, deletion, and improvement of the tables only here inside this database. After refactoring, we moved to that architecture shown with the layers inside our data lake that is now a single storage account, a single blob container, using Databricks as our processing unit, automating the manual transformations that were being made on the Excel sheets into Databricks so that the files would be loaded as CSVs only directly into our landing folder of the data lake. And the process would get the data from SAP to this data lake, and only the data that would be consumed by the application would be loaded into the final SQL server. So the advantages are the one already mentioned when we talked about the advantages of using this architecture approach. We reduced to one data factory synchronized process that now runs in a 20 to 30 minutes, a 50% reduction of the pipeline total time at the least. If it runs a little bit faster, depending on the starting time of the machine, it would be a little less. And summing the increasing costs of this architecture, you might wonder that the storage account will cost a little bit more because we are storing all of the history data in here. This processing unit will cost more because we're putting it into more steps of the process, but we're removing a database. So summing the cost increase of the database and the storage accounts cost increase projections, here we are projecting based on the costs from 1st of July to 10th of July. We expect a reduction of $20,000 yearly by removing the cost of the database and only increasing a tiny portion of the costs with what was more used into here, without counting the benefits of having less maintenance work and all of the others that was already mentioned earlier. So this was the result achieved on DBMS, and that we expect to extend to other products if applicable and if according to the time of the solution, because this framework and this architecture is rather general and not binded to any of the aspects of the DBMS product specifically. The root of the solution is a data layer framework to be used on any product. We need such data layer, and we want to achieve high scalability and reliability. So that's it. Thank you for your attention, and if you have any doubts, please feel free to ask now.
Thank you, Marcelo.
I think.
Oh, go ahead. Go ahead,
please.
No, go ahead.
Oh, okay, so I think my comment is the most generic thing. So like, let me go first before you guys go into detail. First of all, I think this is one of the best lecture I had in my life. It's amazing. Like, I was so surprised. Like, it's great. So first of all, thank you so much for that. And of course, the content, what I mean is achievement is great as well. So yeah, it was really, in a good sense, really surprising. It was great. I was really happy to be here. Yeah. So thank you, Marcelo.
Thank you, Ray.